Hello, a great welcome to this series on engineering mechanics. Myself Jarajan P. This is class 1 of the series discussing on the introduction of the subject. Accordingly, the contents for today's class include 1. Definition and broad classification of mechanics, and 2. The idealizations of mechanics. So let us start class number 1. So let us start with the definition of mechanics. Mechanics may be defined as the oldest of all the physical sciences that deal with the state of rest or motion of bodies subjected to the action of forces. Or in other words, we can say that mechanics deals with the study of the response of objects which are either at rest or in motion when they are subjected to a set of prescribed forces. Now let us see the broad classification of mechanics. So based on the theoretical background involved, the mechanics can be broadly classified as Newtonian mechanics, relativistic mechanics, and quantum mechanics. As the name suggests, in Newtonian mechanics, the laws of motion and the concept of gravity by Isaac Newton forms the basis, whereas the relativistic mechanics is based on the theory of relativity by Einstein. In quantum mechanics, we deal with the small-scale phenomena involving subatomic particles. So this is the broad classification of mechanics simply based on the theoretical basis. Now based on whether we are considering the rigid bodies, deformable bodies, or fluids or gases, other classification of mechanics includes the rigid body mechanics, deformable body mechanics, and the fluid mechanics. We know that a rigid body is the one which theoretically undergoes no deformation when subjected to the forces. And rigid body mechanics, as the term suggests, indicates the study of behavior of such bodies. And the rigid body mechanics can be broadly classified as statics and dynamics. And as we know, statics deals with the bodies either at rest or with uniform motion or uniform velocity. On the other hand, dynamics deals with the bodies with accelerated motion. Then we have the deformable body mechanics, which essentially studies those systems or bodies which deforms under the action of external forces. Finally, we have the fluid mechanics, which studies the behavior of the gases or liquids, which comes under a single name, fluids. Now, the next topic that I want to discuss is a really interesting one, that is the idealizations of mechanics. What are these idealization? We idealize either a physical action or we idealize the system of participating bodies. Why do we do the idealization? Because we simplify our calculations. We simplify the method of coming to our conclusions without any loss of accuracy. So this is what is written over here. In mechanics, the actual physical action and the participating bodies are often replaced with hypothetical. You see the word hypothetical and highly simplified substitutes. And these hypothetical or simply simplified substitutes are known as the idealizations. Some of the commonly used idealizations are: 1. Particle. What's a particle? A particle is a body with mass but with dimensions that can be neglected. And here I want to highlight one very important thing, that the type of idealization we use for a particular problem depends upon the objective of our analysis. For example, in this case, I have introduced a particle idealization in order to analyze the movement of Earth along its orbit. And the question is, why do we use a particle idealization? Because we know that for this problem, I am interested in studying the orbital motion of the Earth around the Sun. So, and in this case, the size of the Earth is very small compared to its orbit. Therefore, this hypothesis or this simplified substitute is acceptable. Then the second hypothesis or the second idealization is known as the rigid body. In many cases, what we do is that when we study the action of a force on a body, we make a simplified assumption that the body which I consider or which I study is rigid. And as I already mentioned, a rigid body is the one that undergoes theoretically no deformation under the action of forces. A practical case is shown here wherein I use the rigid body idealization. Look here. Here I have a simply supported beam that is subjected to an arbitrary load P. Now here I go for this rigid body idealization for the calculation of a support reactions. So this is what I have specifically mentioned in this note. Rigid body assumption in this case is good enough only for the calculation of the support reactions. On the other hand, obviously, if I am interested in calculating the deflection at this point, I cannot go for this what we call as the idealization, because in that case my body comes under a deformable body, so I cannot go for a rigid body idealization. That is what I am repeatedly specifying or telling you, that is the particular idealization used should be matching with the problem under study, and it should happen that the accuracy of the final result is not affected by the simplified assumptions. So now the third idealization is the point force. Now, as you know that what's a point force. So in some cases, what happens is that though the forces that do act on a body is distributed over an area, for simplifying our calculations, we assume that it is not distributed, rather it is acting on a point. So a point force is the one wherein we assumed that the entire load effects are acting at a specified point on the body. For example, I have given here two examples. Look here, this is a body, okay? And we know that as far as the weight of a body is concerned, it is distributed throughout its volume. But for calculations, normally what we do is that the entire weight that is distributed over a weight, it is replaced by a point force, which we call as the self weight of the body, which is essentially acting through its centroid. And here is the second example wherein you can see that a tank that is supported over two pillars. Here we see directly from this figure, yes, the weight of this tank, it is distributed over a certain area of this pedestal. In spite of that, for the calculation of the support reactions R1 and R2, we can assume that these reactions are acting at a specified point on this pedestal. Here again, making use of the simplified substitute known as the point load. So here it is very importantly written another note. Though the weight is uniformly distributed over the volume, it can be assumed to act as a point load through the CG. And we make use of this point load assumption for a variety of calculations that will be performing in the coming classes. So that's all for today's class. Thanks a lot and have a nice day.